Hi, this is Mr. T. This is going to be a pretty concise review of all of the major key topics for the patterns of moon's revolution and rotation. There's 5 key topics. We're going to go in this order in the presentation, so if you want to skip ahead and try to find any single one, you can do that. Otherwise, I'm just going to get started with moon phases and work my way towards tides. So the learning objectives for moon phases are what causes moon phases, identify them from as seen from Earth, what do they look like as seen from space or from orbit, what direction does the moon revolve, and what are the zenith times for each phase. All right, so first off, what causes the moon phases? Moonlight is really just reflected sunlight. So depending on where the moon is in its orbit around Earth, it's going to reflect more or less sunlight towards us. In this instance, you can see that this sunlight over here, although hitting the moon, it's reflecting out this way. And so people on Earth can't see it because they can't see anything on the other side of this red line. So what we'd be able to see is a little bit of this side lit up. We'd see all this light coming back towards Earth, and we'd see a little bit of this dark stuff. So it'd be mostly lit on the right side, and a little bit lit on the nothing lit on the left side. So if the moon changes its position, you can see that here a lot more of the darkness is facing Earth, so we would see just a very small portion of the right side of the moon lit up. Even though 50% of the moon is always illuminated, a lot of it in this scenario is scattered back or reflected back towards space and away from Earth. You can imagine that if the moon were over here, all the sunlight would be reflected back towards the sun and none towards the Earth, and if the moon were over in this position, it would all be reflected back towards Earth. So really, moon phases are a result of the geometry between the Earth, Sun, and Moon, and the angle that's created, which determines how much light is reflected back towards Earth. Here you have a bigger example of them all. This outer ring shows what the moon would look like from orbit, and notice how the same side is always lit up. The side that's facing the sun is lit up, and the side away from the sun is dark. That makes total sense, right? If you have a light shining on something, you're going to light that one side that the light is hitting, and the other side of it will be in darkness. Well, if you're on Earth and looking at this moon, you'd see this entire face lit up. But if you're on Earth looking at it when the moon is in this position, all the light is going back this way, and none of it is going towards the Earth, so you would see darkness. And in between, as the moon revolves around in a counterclockwise motion, you begin to see more light, more and more and more light. This is called waxing, and then you see less and less light, which is called waning. It can be summarized in this graph here. This diagram is relative to the sun, and you can determine the sun's location based off of this picture of Earth, which says that this side of this Earth is lit up and this side is in darkness, which means the sun is coming from the bottom of the screen. So what this means is that because the moon goes counterclockwise, it's going to be growing in light over here, which would make it waxing, and once it gets to its a full moon in this position, it will start waning. The moon, if it's on this side of the Earth, if it's on the side that's closer to the sun, that's going to result in a crescent shape, and if it's on the side of the Earth that is farther from the sun, it's going to result in a gibbous shape. So any combination, using these two combinations, you can figure out what the shape would be. This is going to be a waxing crescent. This would be a waning crescent. Here, this quadrant would be a waning gibbous, and this would be a waxing gibbous. So you can use that to figure out what phase it is. Here, if you're looking at the sun, or if you're looking at the moon, it's in this upper left quadrant, and that means that it's going to be a waning gibbous. And if you look at it, most of the left side of the moon is lit up with a little bit over here of darkness coming towards the Earth, so it would look like this, a waning gibbous. Okay, next, we're going to look at the relationship between the moon's phase, its position in the sky, and the time of day. If you know any two of these variables, you can figure out the third one. So let's summarize basically. This is a nice diagram that kind of summarizes everything. So if you want to take a minute and pause the screen and study it, I think that's a good idea to do. You should also get a review sheet that has this diagram on it, so it's not a bad idea to look at that as well. But let me go into it with more detail. All right, so here are the 3 variables. This picture denotes or illustrates the 5 positions. Remember, all objects in the sky rise in the east and set in the west. And so in the northern hemisphere, this would be facing south, and east would be on your left. This is rise, mid-rise, zenith, mid-set, and then set. There are 8 phases that we'll be looking at. You know, the new moon ranging all the way to the waning crescent with the full moon right in the middle. And then there are 8 times that we'll use these right here. So basically the idea is if you get a picture of where the moon is and its phase, you can figure out what time it is. We know that this moon is shown to be lit on the right side, so it must be waning. It's in the shape of a gibbous, so it's a waning gibbous. And then if you apply that to this model, you can see that a waning gibbous applies in this quadrant of the orbit. So when Earth rotates underneath a moon that's a waning gibbous, everyone on this side of the red line can't see it. And once you cross that red line at 3 p.m., that's when this object, this moon, will begin rising in the sky. And it will keep rising and rising and rising until you're directly underneath it, like this. That's the zenith at 9 p.m. And then it will set when you cross that red line again at 3 a.m. So a waning gibbous is, or I'm sorry, a waxing gibbous is only in the sky from 3 p.m. to about 3 a.m. And it gets higher and higher and higher until 9 p.m. and then begins setting again. Same thing can be applied to this. So here we have a different moon. This time it's lit on the left side, but it's still gibbous. So this must be a waning gibbous. Oh, one more thing. Let's go back to this picture. This picture, this moon is not yet set. It's not at the zenith, so it's mid-set, which means that the time of day would probably be about midnight. It's past the zenith point, but it hasn't set yet, so it's going to be around midnight for that picture. Here we have a waning gibbous, and it's the zenith. So based on that information and applying it to here, you can place your moon at the waning gibbous position, which means that the zenith occurs at 3 a.m. So that picture, in order for that picture to be taken, the person at the red dot would be right about there. Everything is in increments of 3 hours, and that's the major pattern. So let's go back to this picture that summarizes everything. If you know one, such as the new moon that has a zenith at noon, then you can figure out everything else. There's no memorization required. You just have to know that everything increments in 3 hours. So the new moon rises at 6 a.m. It's at the mid-rise at 9. It's at the zenith at noon. It's at the mid-set at 3 p.m. and then it sets at 6 p.m. Now, so those increments of rising, mid-rise, set, and setting, that's all 3-hour increments. If you go to the next phase, all of those 3-hour increments get offset by 3 hours. So the waxing crescent no longer rises at 6 a.m. Now it's rising 3 hours later at 9 a.m. The same thing, the same pattern follows all the way through. So it's a really nice pattern to establish a relationship between those three variables. Okay, patterns with moon's elevation. So the big thing here is the tilt of the Earth. And if we're going to assume the northern hemisphere, then we can figure out that this season is tilted away, the Earth is tilted away from the sun, or the northern hemisphere is tilted away from the sun, which makes it our winter. But notice during a full moon, our northern hemisphere is tilted towards the moon. So whenever we're tilted towards an object in the sky or an object in space, it's going to appear higher to us in our sky. So although the moon would seem low, or the sun would seem low during the daytime, the full moon is going to appear high. Now, because the moon's going to revolve much, much faster on the Earth than the Earth does around the sun, about 14 days from now, this new moon would be down here as well. It would be a full moon. This full moon would be a new moon, which means that, yeah, I guess you can do that right there. Which means that in 14 days, the northern hemisphere is also tilted away from a new moon, so it's going to appear low in the sky. So it all has to do with whether or not the object is, if we're tilted towards the object or tilted away. Here's the opposite scenario. So in summertime, when we're tilted towards the sun, in order to have a full moon, we must be tilted away from that. So a full moon would appear very low in the sky during the summer, but a new moon would appear very high in the sky. So those are your extremes, and then there's also a pattern that results during the first quarters and last quarters and the waning and the waxing. It's basically summarized up in this pattern. The elevation of both the sun and the moon are determined by how much a hemisphere is tilted towards that object. So when you're tilted towards it, it appears higher. And because the moon makes a revolution around us every 29 days, its elevation changes much more than the sun does, which requires 365 days for a complete revolution to occur. So you can kind of set that pattern in here. So this is pretty simple. This is the sun's pattern. In the winter, the sun is low. In the spring, the sun is rising, the elevation. In the summer, the noon sun is very high. And in the fall, the noon sun is getting lower and lower as the weeks pass. The new moon follows that exact same pattern because it's in the same position in the sky as the sun is when we're trying to observe it. The first quarter is going to be offset a little bit. So instead of winter having a very low moon, the moon's just going to be lowering, and then that low moon will occur in springtime. A first quarter will begin rising in the summer, and a first quarter moon will be very high in the sky in the fall. A full moon is the opposite of what the new moon does and the sun, because a full moon is opposite side of the Earth. So a full moon is very high in the winter and very low in the summer. And then a third quarter is kind of getting back, it's changing that thing back to a new moon where it's high in the spring but low in the fall. And you can see this nice kind of diagonal pattern that's occurring. We're low, 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 rising, rising, rising. And it's a nice little summary that pulls out what the moon's elevation does throughout the year. Okay, eclipses. Here, the things you want to know are the types of shadows, umbra versus penumbra. You want to know the types of eclipses, annular, partial, total, the difference between a solar eclipse and a lunar eclipse, and what are the requirements for an eclipse to occur. So first, let's look at the actual geometry of how eclipses occur. During a new moon or full moon, you have the possibility of the moon blocking out the sun and the earth falling in the moon's shadow, or during a full moon, you have the possibility of the earth blocking out the sun and casting a shadow on the moon, and therefore us not being able to see the moon. So eclipse in this sense refers to the object. If it's a lunar eclipse, it means that the moon, lunar refers to moon. If it's a lunar eclipse, the moon is being eclipsed. And if it's a solar eclipse, then the sun is being eclipsed. Okay, but that's not enough. The new moon and full moon, it's not enough because the moon's orbit is tilted about 5 degrees, which means that for most of the revolution around the Earth, the moon is either above the Earth's shadow, or its shadow is above the Earth, or the moon is below the Earth's shadow. So, in order for an eclipse to occur, the moon must also fall on the same ecliptical plane as the Earth and the Sun. That happens at 2 points during its complete revolution around the Earth. This picture here shows the ecliptical plane, which is this big rectangle, and then it also shows the moon's orbital plane, which is tilted about 5 degrees to ours. And at 2 points, here and here, or here and here, and here and here, at 2 points in the revolution is the moon on the exact, and does the moon's altitude intersect with the ecliptic of the sun and the earth. Those 2 points are called lunar nodes, and it's when they line up, and it's when everything appears at the same altitude in the sky. So that's what you need in order to have an eclipse. You need a favorable Earth-Sun-Moon geometry, which occurs during a new or full moon, and you also need the moon and sun to appear at the same altitude, which occurs when the moon crosses the nodes. Those are your 2 necessities in order to have eclipses. So what happens when you do have an eclipse? Well, here's a solar eclipse, and these are the 3 things that can happen. If the moon is close to the Earth, then we'll fall into the umbral shadow, or there will be an umbral shadow on the Earth, and that results in a total eclipse. If the moon is sometimes the moon is a little bit farther away in its orbit, and that results in an annular eclipse, which is when you see a ring of the sun around the moon, and you don't get complete blockage or totality. And then you have a partial eclipse, which is when the Earth doesn't fall on the umbral, but instead it falls in something called the penumbral, and that's kind of like this partial shadow where some of the sun is blocked out, but a lot of it is still visible to Earth. That results in a partial eclipse. Here you have it again. Here's a total eclipse. And sometimes you can get both. So for example, people at this latitude aren't in the umbra, and so they're going to get a partial eclipse that will look like this. People at this latitude will get a total eclipse because they're in the umbra shadow, and then people down here will get in this penumbral shadow, which will result in a partial eclipse. If the Earth were farther back in what's called the antumbra, then you would get an annular eclipse. What's important to note here is that where you are in the penumbra determines how the partial eclipse will appear. In the upper penumbra, you're able to see the top of the sun, and the bottom of the sun is blocked out. In the lower penumbra, you're able to see the lower part of the sun, but the upper part of the sun is blocked out. We did a graphing exercise where we graphed the sun's altitude throughout the year and the moon's altitude throughout the year. What's important is that when the altitudes cross, that's the lunar node. That's when the lunar nodes occur. So once right here and once right there. It's usually twice in a month. I suppose it could happen 3 times in a month, but that's probably pretty rare. All right, let's move on to tides. So some of you weren't here for tides, so I'm going to go a little bit slower here to make sure that we get this. In the tides section, we're going to look at what causes tides to occur, why are there 2 high and 2 low tides that we experience in Long Island or near the Long Island Sound, what are the different types of daily patterns, they're called diurnal, semi-diurnal, and mixed tidal patterns, what are monthly patterns, that's called spring and neap tides, and what moon phases correspond to the monthly patterns. So first, let's look at what causes the tides. There's 2 primary influences. The big one is moon's gravity, but it's not enough just to say moon's gravity, because really what's happening is that it's a gradient, it's a differential felt in the moon's gravity from different spots on Earth. As you get farther from the source of gravity, in this case the moon, the force of gravity becomes exponentially weaker. So the side of the Earth facing the moon feels much more gravity than the side of the Earth that's not facing the moon. That's big. The second thing is the Earth-Sun-Moon geometry. The way the system is aligned can amplify or suppress the tides. I'll explain that in a little bit more detail in a second. Okay, so first off, let's talk about what has more gravity. Clearly the sun is much, much more massive than the moon, so it does have more gravity. But because the moon is closer to us, the difference in how its gravity decreases is much more obvious. And this is due to something called the inverse square law, which says that if you take the square of the distance you are from a source, that's how much the intensity of the gravity decreases. For example, the square of 2 is 4. So 1/4, the gravity here is 4 times less as strong as it is here. If you take the square of 3, it's 9. So the force of gravity here is 1/9 that of here, right? It's not 3 times less, it's 9 times less. It's 1/9 as powerful as it is here. So the difference between 1 and 1/4 is huge. It's a very, very big difference. And the difference between 181st and 1/100th is not as big of a difference as it is here. And that's what I mean by differential gravitation. The difference in gravity is much, much bigger because the moon is closer to us. So it's even though it has much less gravity, its gravitational suppression, the decrease in its intensity is much bigger from one side of the Earth to the other. An example of this that I give is this fire. So if you're standing next to a bonfire, like 3 feet away from a fire, and it's too hot, taking one step back will make a big difference. But if you're already really, really far away from the fire and you take one step back, you're not going to notice much of a difference in the intensity. And that's because of the inverse square law. The change in the intensity is much greater between these distances than it is between these distances, even though the distances are the same. It's just because these are much farther away already. So it's not just the moon's gravity that causes tide, it's the difference in the moon's gravity felt across Earth. Here's how it comes into play. If the moon wasn't there, let's ignore the moon for a moment. If the moon wasn't there, all the oceans on Earth would make this nice ring around Earth, and it'd be equal tides at all locations. But let's say we just plop the moon into existence. What will happen is that the very strong gravity felt on this side of the Earth will pull this water towards the moon, making a bulge. And there's your first high tide. However, we know that there's 2 high tides, and that second high tide comes from the Earth actually being attracted to the moon as well and getting pulled this way. And so once that happens, you get a second bulge on the back side, and you get a bulge on this side, and there's where your 2 high tides come from. It's because the water on the far side, on the near side gets pulled, the Earth gets pulled, and the water on the far side gets left behind. So as a result of tides, as a result of that differential gravitation, depending on where you are and some other aspects like the underwater topography and this concept of resonance, you get a couple different types of daily tide patterns. A diurnal pattern is a single high tide and a single low tide in a 24-hour period. It looks like this graph. So here's your high tide and here's your low tide. A semi-diurnal, which is what we're most used to and which is what most places experience, have 2 high tides and 2 low tides as the Earth rotates once through this. So if you take this Earth and you rotate, let me do this. If you take this Earth and you rotate it once around in a complete revolution, it'll go through 2 high tides and 2 low tides. So that's called semi-diurnal, and that's depicted here in this one. Here's your 2 high tides and your 2 low tides. Typically, they're about the same height, the high tides and low tides, but not exactly. A mixed tidal pattern is a very special case of a semi-diurnal where the 2 highs are very different and the 2 lows are very different. And that's called a mixed tidal pattern. All right, let's move on to monthly patterns. At certain times of the lunation, which is the moon's revolution, the moon, earth, and sun line up to create special tides. So if we take this moon and we put it at a new moon, basically that the tidal bulge that results from the moon lays on top of a tidal bulge that results from the sun. And because the sun is far away, it's not as big of a bulge, but it does exist. And then when you go to 90 degrees to that, a first quarter, these tides, these bulges now kind of conflict, and they kind of suppress the low tides and the high tides. Here again, it's they're amplified, and so you have really big high tides and really big low tides, and then on the third quarter you have really low high tides and really high low tides. So it kind of has this interesting little suppression. These are called spring and neap tides. So just to get the, just to be a little bit more specific, a spring tide occurs when all three bodies are in a direct line. This happens during a new or a full moon. It creates large tidal bulges, and the tidal range between high and low tides is really big. In other words, a really high high tide and a really low low tide. During a spring tide, during a neap tide, during a first and quarter moon, you have tidal bulges kind of offsetting each other and conflicting each other's influence. And this results in a small range between high and low tides. In other words, really low high tides and really high low tides. Here's a nice graph that represents a lot of stuff that's going on. You have the times of day, you have the moon phases, you have what's happening to the tidal range on a monthly pattern. You might want to pause the video here and just kind of explore this, and you can imagine the Earth spinning around at different times and experiencing different things. So as the Earth spins, they'll experience different high and low tides and different high and low tides. And as the moon revolves, those high and low tides will change, as will the phases of the moons and its evolution or its elevation as experienced on Earth. Okay, so that's it for the content. Let's just go over these post-assessment questions really quickly. The correct answer here is going through a phase. Someone asks, Ms. Timmons asked her class to share their ideas about what causes the different phases of the moon, and this is what some of the students said. The correct student would be Sophia. Parts of the moon reflect light depending on the position of the Earth, Sun, and Moon. Some common misconceptions that I saw on your answers are Mona, Drew, and Raj. Raj being the high number. The moon faces Earth a little more each day until it's full, and then it starts to face away. This repeats. This would be true if the moon itself were emitting light, but the moon is just reflecting light. It's like a big mirror. So the same amount of moon faces the Earth every day. What changes is the amount of light that we see reflected off its face. There's parts of this that make sense, but it would only be true if the moon was the source of the light, not a source of reflection. All right, the other question was, 6 friends were talking, and they each had different ideas about why it's warmer in the summer than in the winter, and this is what they said. So the correct answer is Raul, who says it's because the Earth's tilt changes the angle of the sunlight hitting the Earth. But a lot of people put Susan still, which says that it's because the northern hemisphere is closer to the sun in the summertime than it is in the winter. And that's not true. It's totally false. For the northern hemisphere, it's actually the entire planet is much, much closer. Not much, but it's several million kilometers closer to the sun in the winter than it is during the summer. So I can't stress enough that the closeness to the sun, the distance to the sun, has absolutely no bearing on our seasons. Very, very, very little bearing. It's I would say 99% a result of the Earth's tilt that causes changes to the angle of sunlight. Okay, that's it for today. And as always, thanks for watching.